Okay, so this is something to know, and we will also see what happens when if from here I'm not going to consider the lumped element mass matrix. I'm going to go back to the consistent one. When we finish the process, we will then redefine at the global level also a lumped mass matrix. Okay, but this was a useful place to introduce it. Okay, so with those two remarks in hand, let's just return to our formulation, which is the following, right? So we have now the following representation now: integral over omega WH rho right. We've got as far as this. Consistent mass matrix. Okay, we're going to go from here to assembly. All right. Now we do just the same things, the same things that we know from before, right? We say that, okay, my C vector is, going back to our global numbering of nodes. It's C1, C2, up to C number of nodes in the problem. Okay, and this is global degree of freedom numbering. Okay, and the same holds for the D bar matrix, right? D bar again is D bar 1, D bar 2, D bar number of nodes, okay? All right. Okay. Oh, I should be a little careful here. This is not just number of nodes, right? I should be careful here. The size of the C matrix is less than number of nodes. It's number of nodes minus number of Dirichlet degrees of freedom, right? Number of degrees of freedom that have Dirichlet conditions on them, right? Whereas D bar is the full one. Okay, so we have this. What that lets us do is that we can go from here to saying that, all right, if we have these vectors C and D bar defined, then what we have here is C transpose M bar D bar, right? Where M bar is the assembly overall elements of the M bar E matrix, right, of the consistent element mass matrices. Now, this assembly process works just as before, right? Just in the way we assembled our conductivity matrix or the diffusivity matrix, right? Which is that we look at every single degree of freedom, that global degree of freedom that shows up on any element, right? And add the contribution from that element into the global mass matrix. Okay, so so that's it. So let's just recall with a very quick example how that works. Right, it's really no different from, it's identical to what happens with the K matrix, but it's probably worthwhile to just recall. Okay, All right, so as before, element omega E1, omega E2. Let me label the global nodes as maybe A, B, C, and D, and go to the local node numbering. Right, the local node numbering may be 1, 2, 3, 4, 5, 6, 7, 8, and on element E2 we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so with this setting in hand, let's go ahead and look at how the M bar, the global M bar matrix would be formed, right? For those nodes A, B, maybe A, B, maybe C, D as well. But let's see. Okay, so now we go to M bar, right? The global matrix. And let's suppose that the nodes that we're interested in are A, B, C, and D, and those show up here as maybe A, B, C, and D. Okay, so let's look at the contributions to the M to the AA position, right out here. So from omega E1, we would get a contribution which would be M E1, 1, 1, sorry, 2, 2. Plus from E2 we get indeed 1, 1. Okay, let's do another one. Let's do CC. CC would be from E1, ME1, we get 7, 7, and ME2 8, 8. Right, and of course, because node A, global node A and global node C will be shared by other elements besides E1 and E2, there could be more contributions to both of these, right? Okay, let's do the AB term. Yeah, let's do the AB term. So for the AB term, what we see is that from E1, right, from E1 we get the 2, 6 component, and from E2 we get the 1, 5 component. Okay, and maybe other ones too. Other ones from other elements that share nodes A and B. Just to demonstrate the symmetry, let's do the BA term. So this was the, actually I think I already did the BA term. Let's do the AB term now properly. The AB term would be the A row, and the B column, it would be the one here. Okay, so let's see. So if we now look at, oh no, I just realized that I actually did make a mistake here. Everything that I wrote here actually goes to the goes properly to the AB term, right? So I was talking of the BA term, but then I wrote all the AB contributions here, right? So okay, so one needs to be careful about this always, of course. Okay, so the AB term means row A, column B. Okay, so let's do that. Row A, column B would be here M E1 2, 6 plus M E2 1, 5. Okay, and then let's do the row B, column A term, which would be the one here. Okay? So row B column A term would be from ME1 BA, right? So it would be 62 plus ME2 51. Okay, right? And so now we realize that because we've observed already that the consistent element stiffness matrix is symmetric. In fact, the lumped one is also symmetric. Anyway, because the consistent one is symmetric, we realize that the global consistent mass matrix is also symmetric, provided it is square, right? But in general, this thing is not yet square. We need to make it square, right? Which we will. Okay. All right. Now let's go ahead with this right. So essentially, this is how things will work. And what you're observing is that the way you slot in the components of this M-bar matrix is identical to the way we do it for the conductivity or the diffusivity matrix. Okay, that assembly process is exactly the same. Okay, this is a useful place to stop, because all we really need to do when we return in the next segment is talk about how Dirichlet boundary conditions have an effect upon this term, this new term that we are considering. All right.